This course primarily deals with digital communication. Hence, I will begin this session by first introducing you to what an analog signal looks like, and then compare it with the digital signal, and we'll see how a digital signal is different from an analog signal. And then we will also discuss about the benefits of using digital communication. So we'll discuss about why should we go digital, and they will also look at what are the costs associated with doing so. And in the end, you will see that obviously the benefits or advantages of going digital far outweigh the associated costs. So to begin with, let's see, what does an analog signal look like? So typically an analog signal would be like a waveform which is a function of time, and that could be a voltage waveform or a current waveform, but typically we are going to refer to that as an amplitude, right? As far as this course is concerned, we are going to refer to the waveform as an amplitude that is varying as a function of time. So we have an example here where I plotted a waveform which is an analog signal, and what you notice here is that the amplitude of this signal is changing as a function of time. So we have amplitude on the y-axis and time on the x-axis, and the amplitude is changing with time. So, and it's a continuous signal. So an analog signal is a continuous function of time where as far as this course is concerned, we will have amplitude on the y-axis and time on the x-axis. So analog signals are basically continuous functions of time. In contrast, digital signals have a binary representation, or we refer to them as bits. So if you look at the digital signal or digital data, you see they are comprised of just ones and zeros, which are referred to as bits. So we have a stream of bits here. Obviously, these have been obtained from an analog signal by a process called analog to digital conversion. So we begin with an analog signal, and that analog signal is converted through some series of steps into a sequence of bits, which then becomes or represents the digital signal. By doing so, we are getting a lot of benefits, and that is why we go digital. By having a signal in the digital domain or having a signal represented as bits, there are a lot of processes that can be applied which are otherwise not possible in the analog domain, right? So there's a lot of benefits in going from analog to digital, and hence almost all modern day communication systems are digital communication systems. So the question that then arises is, why digital? What are the advantages of going digital? So we'll discuss that. And the first advantage of going digital is what is called as the ease of regeneration. What do we mean by that? The ease of regeneration means that if we have, say, a pulse, a rectangular pulse that is transmitted, and if this pulse is propagating through a communication channel, a couple of main effects happen as this pulse would propagate through the communication channel. One of the effects is that the pulse would get weaker and weaker, so its height or its amplitude will become smaller. And the second effect is that it also gets distorted. That means there would be external noise or interference from other signals which would cause this pulse to get distorted. So it may be something like this, and a further distance away it will be even weaker, and a further distance away and even weaker, and so on. But with a digital communication system, it is possible to periodically regenerate that pulse. So before it is completely disappearing, on the communication channel at regular intervals, we can have what is called as a regenerative repeater, which would reconstruct the pulse and then put it further forward. So This process of regeneration is much simpler in the digital domain with these digital pulses, where the pulse is having a particular amplitude, or the amplitude of the signal will have only two possibilities: one amplitude for a 1 and another amplitude for a binary 0. So as the signal propagates through a communication channel at certain intervals, we can have what is called as regenerative repeaters, which would reconstruct or regenerate the original pulse and then forward it further. So that's one advantage of going digital. The second advantage is that it has better immunity to distortion and interference. So if you notice here, one of the effects that has happened is that as the pulse is propagating through the channel, it is getting weaker and weaker and weaker. That means it's getting reduced in amplitude, and we call that process as attenuation, right? So that is called as attenuation. And then the second effect that you notice is the original pulse is very clean. There is no distortion. The amplitude is flat over the entire duration of that bit. But because of distortion and noise on the communication channel, you see that the amplitude of the pulse is having kind of random variations, right? So that is called distortion and interference, and that occurs due to the noise present on the channel, and also it could be due to interference from other signals that are impinging on the channel. So in a digital system, it is possible to reconstruct or get rid of these effects. And what you notice here is both of these phenomena, that is attenuation as well as distortion and interference, have been negated, and we have got back the original pulse in its original amplitude as well as shape. So the digital communication system offers better immunity to distortion and interference that is coming on the channel. And another advantage of digital is multiplexing. So the multiplexing we mean how do multiple sources share a common communication channel. It could be the signal coming from different users or from different types of signals. For example, on a particular communication channel, you can have different users putting on their signals, or you can have a single user sending his voice signal or video signal or an image. So this multiplexing of multiple signals on the same communication channel is simpler in a digital system, because whether we are dealing with user A's data or user B's data or user C's data, all of them are ones and zeros. So a 1 is a 1 irrespective of who it belongs to, a 0 is a 0 irrespective of who it belongs to. Similarly, if we have binary data coming from a speech signal or binary data coming from a video signal, so the ones and zeros would all mean the same. So the multiplexing techniques used would be much simpler, because irrespective of the type of source from which that binary stream has come, or from the user from whom the stream has come, a bit remains a bit. So the multiplexing process becomes simpler in a digital communication system. And the next advantage is that a digital system has better reliability. Okay, even though we are able to overcome these effects of attenuation and distortion and interference, occasionally it's quite possible that we might have transmitted a binary 1 and the receiver interprets that as a binary 0. This could happen when the noise on the channel is above a certain threshold, and in that case there would be some errors in the received bits. So suppose we might have transmitted 101 and the received signal became, say, 110. So let's say we transmit 101, but the receiver got it as 100. That means there is an error in this third bit, right? And in this digital communication system, we can detect that error and also correct the error. So we have the possibility of detecting the errors as well as correcting the errors, obviously within certain limits. So that gives us the possibility of recovering those errors and getting back our original bit stream. So we call this as error detection and error correction, which is possible in the digital domain, and we refer to that as channel coding. Channel coding, okay, and that is possible in the digital domain. The next advantage of digital is that there are a lot of digital signal processing techniques which can be applied to the binary bit stream to protect it from various problems that can arise over a communication channel. It could be natural phenomena or even by adversaries who are deliberately trying to distort your signal or to steal your data or to get your information. So you can use DSP techniques to overcome all those problems. So we can basically protect our signal from what we call as interference and jamming. So if there is another signal trying to interfere with our signal can be protected by using some DSP technique. And maybe some adversary is trying to jam our signal so that we don't communicate, or we're not able to communicate, especially, for example, in military applications where the enemy might be trying to jam our signal to prevent our communication from taking place. So all of this can be avoided, and our signal can be protected from such effects by using certain DSP techniques. So we can we'll refer to that as protection from interference and jamming. Okay, so the digital domain allows us to do that. And the next advantage is security, wherein we can encrypt our signal so that even if somebody gets hold of our information, they can't really meaningfully interpret our data. So encryption is important. Okay, encryption, and that gives us privacy. Okay, this is particularly important. For example, imagine that you're entering your credit card details and making some shopping on a website. You need to ensure that your credit card number that you're sending to the site is not stolen by anyone and misused. So encryption makes sure that even if someone gets hold of your credit card information, it will be encrypted and garbled so in a manner that they won't be able to interpret what is your credit card number. So that gives you security and privacy. Okay, and the other advantage of digital is compression. By compression, we mean that we can represent our data as compactly as possible. So compression is basically a compact representation of our data. For example, if you have an image or an audio or a video, we can compress this and make it as small as possible. So compact representation of our data. Compact representation of data, and it's also called as source coding. Okay, so that's another benefit of going to the digital domain, where once we convert our signal from analog to digital, we can compress the data so that it contains as minimum bits as possible, and that would mean that the file size would be smaller, so that would require a smaller memory to store that information. And if you have to transmit that information from one device to another device, we have to transmit lesser number of bits because the information or the data has been compressed to a minimal size. So that is typically what happens in practice. For example, you have your an image file, which could be a bitmap image. A bitmap would be having a huge file size, but the moment you convert that to a JPEG image or a TIFF image, the size of the file becomes much smaller, right? Similarly, an audio file could be converted to an MP3 file, which would be having a much smaller size compared to an uncompressed .wav file, right? So compression means a compact representation of the data. So that means it requires less memory to store that information, and also it requires less number of bits to be transmitted when we want to communicate that information. Now, these are some of the benefits of digital. Of course, there are many more benefits of going in the digital domain, but I've listed here some of the basic and important ones. And to achieve these benefits, of course, there are associated costs. Of course, engineering is always a trade-off. You don't get anything for free. So to achieve these benefits, you will always have some costs associated with that. So what are the costs associated in realizing the above mentioned benefits of a digital communication system? So let's look at that. The first associated cost is that a digital communication system requires some intensive signal processing mechanisms to be implemented. For example, if you want to protect your signal from interference or jamming, there is some signal processing that needs to be done, and that could involve some complex computations, and that is a cost associated with digital communication or with digital processing. Another significant disadvantage or the cost associated with digital communication is that synchronization is important. Synchronization means the transmitter and receiver must be synchronized perfectly so that the transmitted bits and the received bits are aligned and we get them in the correct order. Even a slight misalignment can cause major problems, and to achieve that synchronization, a significant amount of resources must be allocated. So synchronization is to, we need to have allocate resources to ensure synchronization. I'll just write synchronization as SYNC. So we need to allocate some resources to ensure synchronization between the transmitter, so we call the transmitter as TRX, and the receiver, which I'll write as RX. Okay, so between the transmitter and receiver, we need to ensure that there is synchronization, otherwise it could cause some problems, and to achieve that, we need to allocate some resources. So there's a cost associated in achieving synchronization. And another cost associated with digital communication is that the quality of or the performance can degrade in a drastic manner. That happens when the channel quality so let me write it as when channel quality degrades below a certain threshold. Right? So when the channel quality or the noise on the channel makes it such that the channel quality is degrading below a certain threshold, then the performance of the digital communication system can switch drastically. Okay, one moment it could be a very good performance, and as soon as the channel quality has gone down below a certain threshold, the performance could go to very bad. So it can switch from being very good to very bad as soon as the channel quality goes below the threshold. So the degradation is not smooth. It can be quite drastic, and that is one disadvantage or that provides or gives an associated cost in digital communication, and we need to deal with that so that the degradation is more gradual. So and in contrast, an analog communication system has a degradation which is much more gradual, but in digital the degradation is quite drastic. And the quality of the channel, typically we measure the quality in terms of the signal to noise ratio, which is the ratio of the signal power to the noise power. And when the noise on the channel is too high, or when the noise increases, then the signal to noise ratio decreases. And once the signal to noise ratio goes below a certain threshold, then the performance of a digital communication system can degrade quite drastically. So that's another cost associated with digital communication. However, if you notice the advantages and the costs, the advantages outweigh the costs associated. So say the advantages outweigh the cost, and that is why almost all modern communication systems are digital. One thing that should be remembered here is that even in a digital communication system, the signal on the physical channel is still analog. So let me write that. Signal on the physical channel is analog. Right? So whether it's a wireless channel or an optical channel or a copper cable, the signal that goes onto the communication channel is analog. So in a digital communication system, the source produces an analog signal which gets converted to digital signal, and in the digital domain a lot of signal processing, compression, error detection and error correction mechanism, and channel coding, which is for error detection and compression, encryption, and a lot of other techniques associated with the digital domain are implemented. And then just before sending the data out from the transmitter, it is converted back to analog, and that analog representation is put on the physical channel. Right? So even in a digital communication system, the signal that goes on the physical channel is still analog. Right? I will stop here, and I will continue in the next part of the video with the first step in a digital communication system, which would be to convert an analog signal to a digital signal, which we call as the analog to digital conversion process, and that would be covered in the following video. Most signals of interest are analog, and therefore in a digital communication system, the first step is to convert the analog signal to a digital signal. And analog to digital conversion is the sequence of steps that we need to perform in order to convert an analog signal to a digital signal. That is, to convert a waveform, which is a continuous function of time, to a sequence of bits, which is binary information. And it's also referred to as A to D conversion. So transforming a signal from analog to digital, which is a sequence of bits, for example, and so on. This process is called as A to D conversion, analog to digital conversion, wherein a signal, which is a continuous function of time, has been converted to a sequence of bits. So continuous in time, as well as it's continuous in amplitude. And A to D conversion translates the analog signal to digital signal, which is a sequence of bits. The steps involved in converting an analog signal to digital signal are as follows. The first step is called sampling. The second step is called as quantization. And the third step is called as encoding. So these are the three steps that need to be performed in order to convert an analog signal, which is a continuous function of time, to a digital signal, wherein sampling is the discretization of the time axis. Quantization is the discretization of amplitude axis or the y-axis. And encoding is the mapping of the discrete amplitude levels to a binary sequence. So it's the mapping of discrete amplitude levels to a binary sequence. So these are the three steps involved in analog to digital conversion, that is sampling, quantization, and encoding. We will discuss each of these steps in detail as we go on, but in this part of the video, our focus shall be restricted to the process of sampling, which is the discretization of the time axis. So we will see what is sampling, what are the rules that we need to follow when performing sampling, and what happens if those rules are not followed. So the first step in A to D conversion is sampling, which is the discretization of the time axis. The process of sampling converts a continuous signal into a discrete signal. So sampling converts a continuous signal, we mean continuous in time, to a discrete signal. The process of sampling takes samples of the continuous signal at a regular instance of time called as the sampling instance. For example, if we denote these markings on the x-axis, on the time axis, as the sampling instance, so that's one sampling instant, that's the next sampling instant, and the third sampling instant, and so on. The process of sampling would take or measure the amplitude of the continuous signal at those sampling instants. So at the first sampling instant, the amplitude of the signal is somewhere here. At the second sampling instant, the amplitude is here. And the third sampling instant has an amplitude of this much. At the fourth sampling instant, that's the sample. So we call the measured value at the sampling instant as the sample of the continuous signal. So that's our next sample, and the sample at this instant is here, and at this instant is here, and at this instant it's pretty much 0, and here also it is crossing the 0, and here it's here, and so on. So in this way, we take the samples of the signal at regular instants of time, and these samples would constitute, would represent what is what we call as the sample version of the signal or the discrete signal. So sampling converts a continuous signal to a discrete signal. So if we just mark those points, it would somewhat be like this. So that would be the first sample, the second sample is somewhere here, and the third sample, and the next sample is somewhere here, and the next is here and here. So we have these samples of the original signal, which are basically the measured amplitudes of the signal at the sampling instance. So that is nothing but the discrete signal. So what we have on top in the marked by the red waveform is the continuous signal, or the continuous waveform, and the process of sampling. So we have performed sampling here, and that gives us a discrete signal. So we can actually put some lines here to indicate that this is the height of each of those points. So that's the next one. So that's basically the amplitude or voltage of the signal at those sampling instance. So this is what we call as the discrete signal. So sampling converts a continuous signal or a continuous waveform into a discrete signal, and that is the first step in analog to digital conversion, which is the discretization of the time axis. So we see in the original analog waveform, the signal is defined for all values of time, but in the discrete version, the signal is defined only for specific instance of time. It is defined at this instant, which is the sampling instant. It is defined at the next sampling instant and the next sampling instant, and so on and so forth. In between the sampling instance, the signal is not defined. So that is basically discretization of the time axis. So rather than having the amplitude of the signal to be defined for all values of time, we have the amplitude of the signal defined only for specific instance of time, called as the sampling instance. So each of these time instance, so each of these points, we call this as the sampling instant. Now a few quick definitions here, are parameters that we need to know. The first one is called as the sampling period, which is nothing but the time separation between two successive samples. For example, the time between one sample and this next sample, right? So that time difference between two successive samples, let me draw that a bit clearly. That would be something like this. So that is called as the sampling period, which is denoted by the letter T subscript S. So TS is the sampling period. So TS denotes the sampling period, and the inverse of the sampling period is denoted as the sampling frequency Fs. So Fs is equal to 1 by Ts, that is the inverse of the sampling period, and we call that as the sampling frequency or the sampling rate. So you can call it as the frequency as well, which is measured as the number of samples taken per second. So these parameters play an important role in deciding or in determining whether we are able to reconstruct our original signal from these samples. So for example, we did sampling and converted this continuous waveform into this discrete signal. Now, what is the condition that we need to follow so that we can get back our continuous waveform from these discrete samples? So in order to be able to reconstruct the original continuous waveform from the samples, we need to follow certain rule, which is given by certain condition on the sampling period and hence on the sampling frequency or the sampling rate. If that rule is violated, then the reconstruction of the original signal from the samples would not be possible. The faithful reconstruction of the original continuous signal from the samples would not be possible if that rule is violated. So what is that rule and how is that rule affecting the process of sampling. While performing sampling, how do we choose the value of the sampling period Ts? So that's the time separation between any two adjacent samples. And how do we determine or choose this value of Ts, the sampling period, and hence the value of Fs, the sampling rate? In other words, how close should the samples be, or how close should successive samples be with respect to each other in order to be able to reconstruct the original continuous waveform from these samples? The answer to this question is provided by what is called as the Nyquist sampling theorem. It is a fundamental theorem in communications and information theory, and the Nyquist sampling theorem gives us the condition that should be followed in terms of determining or choosing the value of the sampling period and hence the sampling rate in order to be able to reconstruct the original signal from the samples. So the Nyquist sampling theorem says that in order to faithfully reconstruct the original signal from its samples, the sampling rate should be at least twice the highest frequency present in the signal. So at least twice the highest frequency component present in the signal. So written mathematically, this condition would be the sampling rate Fs should be at least, so that's greater than or equal to 2 times the maximum frequency present in the signal, which we would denote as Fmax. So Fmax is the maximum frequency present in the signal that we are sampling. For a baseband signal, the maximum frequency component corresponds to the bandwidth of the signal. So let me write that. For a baseband signal, by baseband signal we mean a signal whose spectrum is centered on zero frequency. So for a baseband signal, F max, the maximum frequency components, represents the bandwidth of the signal, which we denote by W. So W is the bandwidth of the signal. So with that notation, we can now write the sampling theorem as Fs to be at least twice the bandwidth of the baseband signal that we are sampling. Or it can also be written in terms of the sampling period by noting that Ts is equal to 1 by Fs. So we can write this sampling equation as 1 upon Ts to be at least 2W, or you can write it equivalently as the sampling period Ts to be less than or equal to 1 by 2W. If this condition is satisfied, then it is possible to reconstruct the original signal from the sample. So that means as long as we have sampled the signal in such a way that the separation between any two adjacent samples is less than or equal to 1 by 2 times the bandwidth of the signal, then we can reconstruct the original signal from the samples. Or put in terms of the sampling rate, the sampling rate Fs should be at least twice the maximum frequency component present in the signal, or Fs should be at least twice the bandwidth of the signal that we are sampling. Or in terms of the sampling period, the sampling period should not exceed 1 by 2 times the bandwidth of the signal. The threshold for the sampling rate, which is 2f max or 2w, is called as the Nyquist rate. So 2f max which is also equal to 2 times the bandwidth for a baseband signal. That is called as the Nyquist rate, Fn. So Fn is nothing but the Nyquist sampling rate, or simply called as the Nyquist rate. So the value of the sampling frequency, if it is exactly equal to the threshold of 2f max, then it is called as the Nyquist sampling rate. In practice, however, a sampling rate greater than the Nyquist rate is chosen for reasons that we will discuss later, but the condition that is required mathematically to be able to reconstruct the original signal from the samples is that the sampling rate should be at least twice the maximum frequency present in the signal. It should not be less than that. It could be more than that, but it should at least be twice the maximum frequency present in the signal. Before we discuss into the effect that happens if this condition is violated, let us quickly work out what an example of finding the sampling frequency for a signal which constitutes multiple frequency components. So let's have a quick look at an example where we have a signal x of t which is comprised of 3 frequency components. So we have a cosine of a frequency f1, another frequency f2, and a third frequency f3. And considering the general notation of the cosine term, which is cosine 2 pi ft, so we can extract the f as, so the f or the f1 here would be 1000 hertz, and the frequency component in the second term, the sine term, would be if you can call this as f2, that would be equal to 1500 hertz, and the third frequency here, if we can call this as f3, that is equal to 2000 hertz. So this signal x of t comprises of 3 frequency components, which we have called as f1, f2, and f3, and the maximum frequency obviously is the frequency component f3, which is 2000 hertz. So f max in this case, f max is equal to the frequency component f3, which is 2000 hertz. So the Nyquist rate for this particular signal, for this x of t, is fn is equal to 2 times f max. It should be equal to 2 times 2000, which is 4000 samples per second. And according to the Nyquist sampling theorem, the sampling frequency fs should be at least the Nyquist sampling rate. That is, the sampling frequency fs should be at least 2f max. So that implies that the sampling frequency fs in this particular case, or for this example, should be at least 4000 samples per second. If this condition is violated, then a kind of distortion occurs, which is called as aliasing. So if the sampling rate fs is less than the Nyquist rate, which is 2f max, a distortion occurs, which is called as aliasing. So aliasing occurs. What is aliasing and how do we understand aliasing? We'll look at that very shortly. So when the condition imposed by the Nyquist sampling theorem is violated, a distortion called aliasing occurs. And what is aliasing? Aliasing is nothing but the mapping of some higher frequency components in the signal onto some lower frequency components. So it's the mapping of some higher frequency components onto lower frequencies. In other words, if the sampling rate is less than the Nyquist rate, then upon reconstruction of the signal from its samples, there would be some frequency components which originally had a higher value. Those would get reconstructed as some lower frequency values, and this is what is called as aliasing. We'll discuss about aliasing with examples and demonstrate the process of aliasing with examples and illustrate which frequency component or which higher frequency component gets mapped to which lower frequency component depending on what is the sampling rate. I will illustrate that with examples in later videos, but for now let us try to understand what is aliasing, and to understand that we need to look at the process of sampling in the frequency domain. So when we perform sampling of the signal in the time domain, what is the effect of that process in the frequency domain? So to understand that, I would like you to recall from my earlier video on the topic of spectrum and Fourier analysis, the relationship between time and frequency domains. So suppose we had we denote the time domain T and the frequency domain as the F domain. Then if we recall from the lecture on the spectrum and Fourier analysis, where we showed that when the signal in the time domain is periodic, the spectrum of the signal or its frequency domain representation is discrete. And by duality of the Fourier transform, the signal in the time domain, if it is discrete, then its frequency domain representation becomes periodic. And what is it that is happening in the process of sampling? In the process of sampling, a continuous signal is being converted into a discrete signal. So the process of sampling is making the time domain signal discrete. So the effect it's going to have on the frequency domain representation of the signal is that the spectrum of the sample signal is going to be periodic. So we will use this fact and depict the process of sampling in the frequency domain without going much into the mathematical details of the process itself. So hence we can say that discretization of a signal in the time domain has the effect of introducing periodicity in the frequency domain. And we will use this idea to understand the effect of the process of sampling in the frequency domain, and then we will also see how the value of the sampling frequency Fs is going to affect the spectrum of the sample signal, and thereby we will be able to see what is the meaning of aliasing. So therefore, the process of sampling in the time domain has the effect of making the spectrum of the sample signal to be periodic, and the period of the spectrum is equal to the sampling frequency. That means the spectrum of the sample signal has spectral replicas at integer multiples of the sampling frequency fs. So consider the signal here x of t, which is the continuous signal given by this red waveform, which has a spectrum where we have plotted the magnitude spectrum of it, and the spectrum shows that the maximum frequency present in this signal is a certain f max. So that means the highest frequency component in the signal is f max. Now, when we perform sampling on this signal, it discretizes the signal, so the continuous waveform becomes discrete. So going from here to here, it is performing the process of sampling. So that gives us a discrete signal in the time domain. So that is discretizing the signal. So the red waveform is continuous, and after sampling, what we get is the amplitudes at the sampling instance given by these black dots, and I have put these black dots separately here, where the height of each dot above the x-axis is basically the amplitude at that sampling instant. So as a result of discretizing this signal in the time domain, what is the effect that we see in the frequency domain? So what we have on top here is the original spectrum, or the spectrum of the original continuous signal shown in red here. And what we have at the bottom here is the spectrum of the sample signal, or the spectrum of the discrete signal. And as we have mentioned earlier, discrete in the time domain corresponds to periodic in the frequency domain, where the spectral replicas or the spectrum has replicas at integer multiples of the sampling frequency fs. So that means the spectrum of the sample signal, which we are denoting by the letter xs of f. The magnitude spectrum of the sample signal is xs of f, and the corresponding notation that we have used for the time domain representation of the discrete signal is xs of t. So the spectrum of the sample signal would have a periodic repetition of the spectrum of the original signal. So the original signal had this spectrum, and as a result of sampling, the spectrum would become periodic, where the replicas occur at integer multiples of the sampling frequency. So there is a replica here at 0, so because that is centered on 0, it's a baseband signal. And the first spectral replica occurs at 1 times fs. The second replica occurs at 2 fs, and so on, and it goes on to infinity. And similarly, on the negative side, you'll have a replica at minus fs, and the replica here at minus 2 times fs, and so on. So what we see is that as a result of sampling, the spectrum of the sample signal becomes periodic. So discretization in the time domain is introducing periodicity in the frequency domain. Now, the spectrum of the sample signal that I have drawn here refers or depicts the case where the sampling frequency fs is greater than 2f max. How do we know that? Now, it is very intuitive looking at the diagram itself. So this distance here from 0 up to here, that is f max, and again from the center here of the first replica to the edge here, so that distance is also f max. So the total distance here is fs. So we have an f max over here and f max over here, plus there is a spacing, an extra space here, so that is f max plus f max, so that's 2f max plus some extra space here between these replicas, which means that the sampling frequency fs here, where the first replica is occurring, is greater than 2f max. So the spectrum that has been shown in this particular diagram corresponds to the spectrum of a sample signal where the sampling has been done at a rate greater than the Nyquist rate. So fs is greater than 2f max. So that's the spectrum for the sample signal where fs is greater than 2f max. So let me highlight this, right? So how do we know that? Because this distance here, just to re-emphasize, so this distance here is f max, and this distance here is also f max. So f max plus f max, that's 2f max, plus some extra spacing here. So the total distance starting from 0 to fs is going to be 2f max plus this extra spacing, whatever that is. So basically we have this condition here that this is the spectrum for the case where the sampling rate is more than the Nyquist rate 2f max. Now, if the sampling rate was exactly equal to the Nyquist rate, that is fs exactly equal to 2f max, then what you will see is that these spectral replicas would be touching each other. So there won't be any space between them, between these replicas. So I'm just going to quickly draw it by hand. So the condition or the spectrum for the case, let me change my ink. So if you have a signal which has been sampled at exactly the Nyquist rate, then the spectrum of the sample signal is going to have replicas that are going to be touching each other without any gaps between them. So it would be the same on the negative side, and these go on till infinity. And I must mention here that the example that I'm depicting here is for the case when the sampling is done in an ideal way. In practice, however, ideal conditions are not met. But for the purpose of understanding, we'll restrict our analysis and explanation to the ideal case. So that's our frequency axis, and that's the spectrum of the sample signal, or the magnitude spectrum of the sample signal, where we have the spectral replicas at integer multiples of the sampling frequency. So that's 2fs, that would be minus fs, minus 2fs, and so on. And because this distance here is equal to f max, and this is also equal to f max, so that makes it the distance fs to be exactly equal to f max. So we have the condition here that fs is equal to 2 times f max. So this case here, the spectrum which is shown here corresponds to the spectrum of a sample signal where the sampling rate is exactly equal to the Nyquist rate to f max. Now, if the sampling rate is reduced any further, what we expect is that the spectral replica which occurs at fs and 2fs, they are going to move inwards, and that means there's going to be an overlap with the previous replica or the previous copy of the spectrum, or the previous replica of the periodic repetition of the spectrum. So let's draw the spectrum of the sample signal where the Nyquist criteria or the Nyquist sampling theorem is not satisfied. So in this case, we're going to have the original spectrum as it is, and then the replicas are going to have overlaps because the sampling rate is less than 2f max. So this is when aliasing is going to occur. So that's the frequency, that's the spectrum of the sample signal when fs is less than the Nyquist rate, which is fs less than 2f max. So similarly, we are going to have a replica on this side and a replica on this side, and so on. Okay, so that's 0. That's the first replica occurring at 1 fs, the second replica at 2 fs, the third replica at 3 fs, similarly here at minus fs, minus 2 fs, and also minus 3 fs, and so on. So minus 3 fs and so on. So clearly from this diagram we see that that distance is going to be fs, and that distance is going to be f max, and that distance here is fs, and clearly fs is less than 2f max because of this overlap here. So this constitutes, or this depicts, the case where the signal has been sampled at a rate below the Nyquist rate. So the spectrum of the sample signal shows replicas which are overlapping with each other, and these overlapping regions here, that is what depicts the aliasing part, so the aliasing distortion. So these are what depicting the process of aliasing. So all right, so to summarize, sampling is the first step in analog to digital conversion, whereby a continuous signal is converted into a discrete signal. So basically it's the discretization of the time axis. Now the effect this process has on the spectrum of the signal is that the spectrum of the sample signal becomes periodic with a period equal to the sampling frequency. That means the spectrum of the sample signal has replicas which occur at integer multiples of the sampling rate, fs. And depending on the value of fs, the spectrum may have, the spectrum of the sample signal may have replicas which are spaced apart from each other, or it may have replicas that are exactly touching with the boundaries, at the boundaries, or they can have overlaps, as in this case, in which case it has violated the Nyquist sampling theorem, and that causes aliasing. Now, as I mentioned earlier, aliasing is the mapping of some higher frequency components onto some lower frequency component. So what we notice when we compare these spectral diagrams of the sample signal is that the case where the sampling rate was more than the Nyquist rate, there was a gap between these spectral replicas, and when the sampling rate is reduced, these spectral replicas are moving inwards. So when they move inwards, they are coming closer to each other. So that means the higher frequencies are moving on to lower frequencies. And even in this case, where the sampling rate is exactly equal to the Nyquist rate, there is no problem, because even though the replicas have moved inwards, they are not interfering with the earlier replica or the previous replica. They are not overlapping with each other, and therefore they do not cause any distortion. That is true in the mathematical sense, but in practice, however, it is desired that there is some gap between the spectral replicas for practical purposes, which I will discuss later. But for now, let's stick to the basics, where this is also a sufficient condition to reconstruct the original signal from its samples. But when the sampling rate is reduced below the Nyquist rate, these replicas move further inwards and overlap with the previous spectral replicas, causing what is called as aliasing distortion, as we have depicted in this particular diagram. So aliasing occurs here, which is nothing but the mapping of higher frequencies onto some lower frequencies. So with aliasing, higher frequencies will reconstruct as some lower frequency. right? So that's the concept of aliasing and the Nyquist sampling theorem and the effect of sampling in the frequency domain and what happens if we violate the Nyquist sampling theorem. Okay, we will stop here, and in the next lecture or video, I will be discussing in more detail about aliasing and show exactly which higher frequency maps onto which lower frequency, and that would depend on obviously on the sampling rate and the frequency components present in the signal, and we would illustrate and show how higher frequencies get mapped onto lower frequencies, resulting in aliasing.